So the three topics for today were exponent gymnastics, that's this first one, followed by quadratics, followed by rational expressions. So let's get going. Spot the error on this one. So if I simplify this combination of exponentials, I might take this negative 1 power and distribute it across the multiplication inside the parentheses like so. Same thing with the power in the denominator, this third power. And then I'd reduce some exponents, like I had a power of s and a power of s, get those together, denominator, simplify my powers of r. And then at the end of the day, I have some negative exponents, and so I probably want to write my answer using positive exponents instead. So I'll just shunt those powers into the denominator. So what did I screw up here? If you look at this solution, which step did I go wrong? The step that I made an error on is right here. R to the negative first power, r to the negative ninth power, and I combine them together to make r to the negative 10th power. Why is that incorrect? I should be subtracting, and how do I know I should be subtracting the exponents instead of, as I did here, adding? Right. Dividing powers means subtracting exponents. Adding exponents means I'm doing what to the powers? Multiplying, right, exactly. Yeah, I said it the other way around. If I'm multiplying powers, I add exponents. If I'm dividing powers of the same base, right, I'll subtract exponents. So what exponent should r have had here instead of negative 10? Negative 1. Negative 1 minus negative 9. Yeah, you're right, it's positive 8. Great. So, right, dividing powers, we should subtract the exponents. Negative 1 minus negative 9, that's positive 8. And so, if I repair this, I'll get an 8 here. And so then how should my final answer appear here?
R8 over S4?
Yeah, I'll take that 8th power of r and I'll leave it upstairs in the numerator. R to the 8th over s to the 4th. Yep, cool. So notice that we did a lot of different types of exponent gymnastics along the way. I distributed powers, which, by the way, how do I know I can distribute an exponent? When is that okay? Yeah, but what needs to be on the inside of the parentheses to make that okay? What's the operation that's connecting the r with the s squared and the r to the minus 3? Yeah, it's multiplication. Exponents distribute over multiplication. Remember, they don't distribute over addition or subtraction. Right? That was one of our common errors from last week. So I distributed the powers, and then from there on, it was just a matter of multiplying powers by adding the exponents and dividing powers by subtracting the exponents. For our next trick, this is using factoring to solve quadratic equations. We're going to pick on question number 2. R squared plus r equals 20. So I look at that and I say, let's factor. R squared plus r is r times r plus 1. And so then now that I have it factored, I can split apart those two factors. Each one of them gets an equation, solve those simpler equations, and we're done. What did I screw up? We could very easily check that these are not correct solutions, right? We could try plugging them back into the original equation. If r is equal to 20, r squared is 400. Add 20 to 400, we get 420, but the right-hand side of this equation is not 420. So clearly, we can check to see that our solutions are not, in fact, solutions. And the reason that we screwed it up is that we cannot split a product of two factors into their own separate equations unless the right-hand side of that equation was 0. Exactly. We need that 0. It's the magic number on the right-hand side because it's the only real number that has a uniqueness in its factorization. Right? 0 is the only real number which we know for sure what one of its factors must be. 0. Right? 20, there are infinitely many different pairs of factors that multiply together to give me 20. Right? 4 and 5, 20 and 1, negative 20 and negative 1, but also, let's see, 3 halves and, why am I doing this on my feet? So there's a whole bunch of different pairs of real numbers that multiply together to give me 20. Infinitely many of them. But 0 does not have that property. 0 has a unique factorization. So what should I have done here? How do I fix this mistake? Subtract 20. When? Immediately. Yeah, don't even think about factoring until one side of that equation is equal to 0. So I made an error from the word jump on this one. R squared plus r minus 20 equals 0. And now I should factor. How does r squared plus r minus 20 factor? 5 and 4. Let me erase this thing that's underneath it here. How do I do the pluses and minuses on that? Minus 4 and plus 5. Great, because I need a pair of numbers that multiply to negative 20 and add together to give me positive 1. And now, because the right-hand side is 0, now it's okay to split the two factors. Because I cannot multiply two real numbers and get 0 unless one of those real numbers was 0 in the first place. Yeah, right. So one of my factors is r minus 4. I set that equal to 0, and I solve and get r equals 4. And then my other factor, r plus 5, I solve that for r, and r is negative 5. Yep, there we go. Okay, cool. So in our last example, we just have to add a couple of rational expressions. I'm going to pick on problem number 4 here. 2 over x plus 4 minus x plus 2 over x minus 4. So what's the first thing I want to do? I want to find a common denominator. This is something that anytime we're adding or subtracting any kinds of fractions, even when those fractions happen to have expressions in them, we need a common denominator before we can add. So I'll find a common denominator. The quick and dirty way is just by multiplying the two denominators together, right? Once I multiply the two denominators together, here's how I like to keep track of things. I keep the original denominator over its original numerator over its original denominator, original numerator over its original denominator, and then I can kind of see, oh, okay, this x minus 4 is new, so I need to put an x minus 4 up there. That x plus 4 was new, so I'll put an x plus 4 up there, right? And remember, at this step, you can always check your work by imagining what would happen if I canceled this x minus 4 factor with that x minus 4 factor. I would just get this original thing back, right? Same thing with this x plus 4 factor. Cancel those, we get back there, right? So that's all we're doing, right? And now, once I've set up the common denominators, their difference, if I subtract, is going to have that same denominator downstairs, so I'll just rewrite that. And then to simplify the numerator, I'm going to start by simplifying these products. 2 times x minus 4, 2x minus 8. The other product, x squared plus 6x plus 8. And then I'll just subtract 2x minus 8 minus that thing. I'm going to get the x squared gets a minus sign, and then the number of x's, I have 2 here and 6 there, so that makes 8. And I have a negative 8 here and a positive 8 there, that makes 0. Simplify that out. Minus x squared plus 8x, I'll factor that thing. We're done.
There's no error.
There's an error.
Oh, okay.
There is an error. Where is it? Where did I mess this up?
You're supposed to minus the x squared plus 6x plus 8.
Ah, yes. So what should I have done? So it's you're saying it's at this step here, right?
Yeah.
What should I have done to have avoided the error that I made here?
Subtract everything from the green. Because
Right.
negative 1 times that.
Yes, exactly. So this whole thing written in green here, that numerator, all of that needs to be subtracted from 2x minus 8. So one way to look at it is we could sort of bookkeep like this were a second grade subtraction problem, right? 2x minus 8, and I'm going to subtract x squared plus 6x plus 8. Right? I'm just going to put a big subtraction sign in front of that and imagine, what happens, right? I'm going to get, nothing minus x squared, so I do end up with a minus x squared. But then I'm going to get 2x minus 6x. So I should have had negative 4x. And negative 8 minus 8. No.
Oh.
Yeah, negative 16. Yeah. So, right. So I need to subtract that whole second numerator from the whole first numerator, right? The other way that I recommend, so there's a couple ways. The way that you mentioned is instead of thinking of it as a subtraction, think of it as an addition of negative 1 times that quantity. Right? So that's the way to handle subtraction, right, of something that has multiple terms. Or if you're comfortable with a little bit less notation, just remember to put parentheses around that, right? And then when you go to subtract, you can put in the negative 1 as a coefficient in front if you like to and make it into an addition problem. But usually, if you put the parentheses in there, it cues your brain into remembering, oh, this minus sign needs to distribute to all 3 of these terms on the inside. So yeah, what we do end up getting then is minus x squared, yes, but then minus 4x minus 16. Oops. Minus 4x minus 16. And if we wanted to, we could factor a minus 1 out of that whole thing. But then, I think we're done. All right. X squared plus 4x plus 16. Because that doesn't have any factorization over the integers that I know of. And you can, if you want to, at the end of this problem, multiply out the denominator and get x squared minus 16. I really don't care, right? It depends on what you're doing with this expression at the end of the day. I like to, whenever possible, leave things factored for as long as possible, because stuff that's in its factored form is much easier to understand. And particularly when we start looking at functions that are built on top of these kinds of expressions, a lot of what we care about in the properties of those functions, we can only tell from the factored form of these expressions. So get things factored, leave them factored as long as you can, and it'll be much easier to understand down the line.